We have a prototypical geometric optics problem, meaning that if you can understand this one well, then you will have an easier time understanding many other similar optics problems. There's many such problems. They'll continue on forwards, not just in mirrors, but also in lenses as well. And so in this case, we have a mirror represented by this blue curved line, and we have an object, and that object is going to reflect off the mirror, and this light is going to go, well, kind of everywhere, right? Bounces off in the mirror, but there's one location where these lines, these light rays that come off the object and reflect off the mirror, they'll converge and form a focused image, which we call just the image. So this is a very common setup, not just in mirrors, but in lenses as well. And so let's get to reading here. A 2-meter tall person, right here, that's our object, is 12 meters away from a 500 millimeter mirror. That 500 millimeter mirror, that's really referring to the focal length. You may think that we're talking about the radius, but no, that 500 millimeters refers to the focal length of this concave mirror. Where is the image of the person and how tall is it? What is the magnification and is the image inverted? So I've provided these equations are all you'll really need, and actually a little bit more than what you'll need in order to solve this problem. So why don't we look back at our notes at what a geometric computation here, like a ray diagram, looks like for a concave mirror. You don't have to memorize these, but what I would say is try to memorize what these lines do and how you can construct the image on your own. And in this case, there's 3 lines that will help construct the image. The first is the green one is a line that's parallel to the optical axis. That's this line. That one will end up always going through the focal point. The line that goes through the focal point will end up parallel. And the last is the line that goes through the radius of the mirror. That one will bounce right back because this is like, 90 degrees perpendicular to the mirror. And all 3 of those lines will converge at one point, which is where the image is created. These 3 equations will work for mirrors. We'll see that they are identical to lenses as well if you are careful about minus signs. But the 3 equations here are the focal length. This one's related to the focal length. This one connects your object and image distances to their heights or their size. And this one is just saying, putting that into a value, a unitless number, m, the magnification. So let's just go ahead and get started. And mostly this is a question about identifying and then plugging and chugging and solving this upside down equation where everything is reciprocated, which is very fraught with errors, very easy to fall into the pitfalls. So where is the image? That sounds like a DI. DI is a where, it's a location of the image. And how tall is it? That sounds like an HI, the height of the image. Okay, so let's start there at looking for that DI. We have everything we need in the first equation. 1 over F equals 1 over DO plus 1 over DI. So let's confirm here. F, do we have an F value? F is the 500 millimeters or 0.5 meters. Right here, by saying that it's a 500 millimeter mirror, that is saying that F is 500 millimeters for that mirror. DO is the object distance. If you look at the graphic here, DO is the distance from the mirror to wherever the object actually is, which in this case is not 2 meters, that's the height of the person, it's the 12 meters, and so DO is 12 meters. I'm going to take an approach where I just plug things in and then solve for DI. In this case, And so, not the only way to solve the problem, but I think a sort of straightforward way if you've got your calculator handy. So 0.5 meters, 1 over 0.5 meters equals 1 over 12 meters plus 1 over di. And we're going to solve for di. To solve for di, I think the easiest thing to do would be to solve for 1 over di first. And so first let's just plug these into a calculator. 1 over 0.5, well that's just 2. And it's not going to be 2 meters. Okay, since meters is on the denominator, it's actually going to be 2 times meters to the minus 1. 1/12, similarly, is not going to be, well, let's see, give me a second here. It's going to be 0.0833, but it's not going to be 0.0833 meters. It's 0.0833 inverse meters, and that's what we're adding to 1 over di. And we're going to subtract out the 0.083 from the other side, and we get 1.917 inverse meters is equal to 1 over di. If you're in this situation, you've got, if you've got your units attached, something should be ringing in your head that meters to the minus 1, that's not a distance. And so we're not done yet. You need to solve for di. Since 1.917 equals 1 over di, then that means di is equal to 1 over 1.917. Essentially just reciprocating both sides. And now we have the inverse meters on the bottom. And so if you do this division, they'll end up on the top. di is equal to 0.522 meters. Just a little bit beyond the focal point, which makes sense. 0.522 meters equals di, just a bit beyond the focal point. And that's part A. That's part A. We're done with part A. That is the, nope, we're not quite done with part A. Actually, we've got the distance, but we still need how tall is it. And surprisingly, you can get that from the distance. You can look back at the notes and figure that this comes from looking at similar triangles in geometry. But we can solve for hi in that equation. Now we know everything we need because we already discussed. So HO is the height of the object. That's going to be the 2 meters, 2-meter tall person. DO is the distance. That's the 12 meters. And we don't know HI, but we now know that DI is 0.522 meters. So to get HI by itself, I can multiply both sides by DI. So multiply by DI like this, and multiply this side by DI as well. And multiply by a -1 as well. And so HI is equal to negative DIHO over DO. And the image distance, so let's put everything in. Image distance is what we just found, 0.522 meters. HO, the height of the object, is 2 meters. And DO, the distance to the object, is 12 meters. Plug everything in. HI is equal to negative 0.087. And now we could actually already answer part C. 0.087 meters. Let's keep those units attached. We can answer part C, that since this is a negative value, that means that the image is inverted. As we can see from our diagram, we end up that the arrow is upside down. We have an upside down image. Okay, so let's double back to part B. What is the magnification? So just from a simple point of view, the magnification is the image height divided by the object height. That's exactly what the magnification means, right? That this part of the equation is like, how much has it been magnified? And so it is a unitless number, and it doesn't take much. I can even put it into this little corner here. M is HI over HO. HI is the negative 0.087 meters, and HO is the object height, which is 2 meters, and so m, the magnification, is negative 0.04 or so. Unitless value, negative 0.04. Multiple ways to get it though. You could have used the distances instead, di and do. You just have to remember to put the negative sign. But this is it. This is a sort of general problem which you may see multiple times, and so I would say if any of this didn't make sense, then take it slow and write down any questions that you have to ask me in the future. Hopefully that made sense. We will see you in the next one.